Crystal field theory in tetrahedral complexes. We know that in a tetrahedral complex, there is the central metal atom attacked by or surrounded by 4 ligands. Ligands, as you know, are electron donors. Now, the degenerate d orbitals, 5 of them having the same energy. That is why we call them as degenerate orbitals. When a ligand approaches the degenerate orbitals, it will have an increased average energy. And then the orbitals split into 2 sets. One having 3 orbitals with them and the other having 2 orbitals. The one having the 3 orbitals, that is the dxy, dyz and dxz orbitals, are going to a higher level or having an increased energy. That is the T2 set. And the 2 orbitals dx square minus y square and dx square, that becomes the E set. So always notice that it is not T2G but it is T2 and E, because in the case of these tetrahedral complexes, they lack that symmetry. That is why it is given as T2 and E, avoiding that G, T2G is not used or EG is not used. Now you know that these ligands which are approaching the central metal atom are not coming along or not aligned to the 3 axes. They are coming along the interaxial orbitals. So the interaxial orbitals are dxy, dyz and dxz. That is, the lobes of those d orbitals are lying between the x and y axis, z and y axis, and x and z axis. In the previous case, that is in the case of octahedral complexes, those ligands were approaching along the axis, and the d orbital lobes which were lying along the axis were having an interaction much more, or the repulsion between the electrons was much more in the case of octahedral complexes, and the orbitals affected were dx square minus y square and dz square. But in the case of tetrahedral complexes, it is the d orbitals lying between the axes. That is the interaxial orbitals. Those electrons are getting more repulsion, or these lone pairs on the ligands and the electrons in the d orbitals which are lying between the axes are getting repelled. So the T2 set has the dxy, dyz and dxz orbitals. They are triply degenerate. Triply degenerate means 3 orbitals which are having equal energy, and dx square minus y square and dz square, they are doubly degenerate. That is 2 orbitals having similar energy or same energy. Now we are assigning delta T is the unit, or delta T is the separation energy between the 2 sets of orbitals. That is the T2 set and the E set have a separation energy of delta T, where T represents tetrahedral complexes. So we know that the line which separates the 2 sets is called the barycenter, and the one above the barycenter is having a higher energy of 2 by 5 delta T. That is, each orbital is having that much of energy, and the one lower to the barycenter is having a lowered energy of minus 3 by 5 of delta T. Now this is for each orbital. Now you know that 2 by 5 is equal to 0.4. This is what we use in the calculation of the crystal field splitting energy. For calculating delta O or delta T, we use this factor, and here it is 0.6. For each electron in these orbitals, we multiply these factors by the number of electrons in these orbitals. That also you know. And dq, that is the differential of quanta. Energy difference between the two sets of orbitals are represented by this quantity, that is dq, that is actually differential of quanta. Now almost always delta T is less than delta O. Delta O is the splitting energy for octahedral complexes, and delta T is the splitting energy for tetrahedral complexes. Now in the case of delta T, that is for tetrahedral complexes, there is more repulsion in the d orbitals lying in the interaxial orbitals. And another factor which is responsible for this difference, that is the delta T less than delta O, is that the number of ligands here are only 4. There are only 4 ligands. So the number of electrons, as you know, will be lesser. In the case of octahedral complexes, you know, there are 6 of them, 6 ligands approaching the central metal atom. So that is why there is a difference between delta T and delta O. Delta T is less than delta O. Then the repulsion of the electrons in the d orbital lobes and the coming ligand molecules. See, when these orbitals are lying in the between the axes, the probability of them having a head-on interaction is less, whereas when the orbitals are lying on the axis and the ligands are approaching along the axis, there is the possibility or probability of more interaction between the electrons. So there the electrons are repelling. That is why there is a more energy separation. There is more energy separation in the case of O, that is octahedral complexes, whereas the separation energy is less in the case of tetrahedral complexes. I hope it is clear.